This project has been done in collaboration with a few people, including myself, Alexander Winter, and Paul Cry, all from McGill, as well as David Levine from the University of Toronto. Physics-based animation allows users to generate delightful complex emergent behavior and deformation motions. In standard simulators, this computation of deformation is expensive, forcing an a priori choice of whether the object should be simulated as a rigid or a soft body. In dynamic scenes, such as this one, there are often many non-deforming elements, like these tentacles moving rigidly, or the head of the octopus at rest in the bowl. There's an opportunity to target those regions to greatly speed up the computation time. Many beautiful techniques aim to speed up the simulations by approaching the problem from different angles. For instance, there are multi-resolution methods that use hierarchies for adaptive refinement. Model reduction has been a successful approach for generating fast, low degrees of freedom elastic simulations. Sleeping in the inertial frame is also a valuable technique for saving computation time. Instead, we take a fundamentally different approach. We simulate elastic solids as rigid bodies when they are not deforming. With our method for on-demand elastification, simulations become properly input sensitive. The rigid versus elastic modeling decision becomes a function of physical parameters and environmental interactions rather than a guess made prior to runtime. Our approach is hierarchy-free. We instead use connected components. This gives us maximum flexibility for which part of an object can be treated as rigid. So, very complex object can reduce to a set of rigid and elastic parts that often simulate an order of magnitude faster with visually consistent results. For this octopus, we can trivially handle the static regions, such as the head, but also provide rigidification in the tentacles as they swing. But what happens if we pull on one of its tentacles? Well, the tentacle elastifies, allowing a detailed simulation of the deformable motion. Next, I will describe our method in three main parts: rigidification, elastification, and threshold selection. To rigidify, we need a good measure of deformation. The green strain is a perfect fit by being invariant to rotations and translations. We can rigidify an elastic object when we see that the time derivative of the strain is zero. However, a problem is that the strain rate for rotational motion is non-zero if we compute E dot with the vertex velocities. This happens because the velocities step the vertices along linear paths in a manner that shrink and grows the material over the time step. That is, they don't match the instantaneous rigid velocities that would provide a zero strain rate computation. So instead, we avoid this problem by computing the strain rate using finite differences. Here we see a cantilever simulating with both elastification and rigidification. Let's focus on the rigidification as I will explain elastification later on. The dots show each element's strain rate on a log scale. There is an opportunity to rigidify when the dots are bright green. See how the cantilever and dot colors oscillate with elastic waves. We set the threshold on the Frobenius norm of the strain rate to identify what element can become rigid. This threshold can be seen as a speed limit on deformation. We are now able to detect what to rigidify and tag the elements for rigidification. Next, we need to group them into rigid bodies. To do so, we must find sets of connected components. We pre-compute an element adjacency matrix before the simulation. We then use a breadth-first search on the adjacency matrix and explore only the rigid elements to make our rigid bodies. This step has a linear overhead, which becomes increasingly negligible as the scene grows in number of elements. Once we have the connected components, we loop over all vertices to compute the mass properties, coordinate frame, position, and velocities of each rigid body. Here, the linear and angular body velocities are computed to match the elastic degrees of freedom, and rigidification exactly preserves momentum if the elastic region has perfectly rigid motion. Each newly created rigid body greatly reduces the size of the system to solve by transforming many elastic degrees of freedom into a small constant number. More precisely, in this 2D example, we turn twice the vertex count in the orange region into exactly 3 degrees of freedom. The coupled system is easy to solve. Elastic elements that touch the boundary of a rigid body now simply use vertices that are kinematically mapped to the rigid body. At some point in the simulation, rigidified elements could try to form a hinge. For instance, this element could be tagged for rigidification, but if it was part of the green rigid body, it would share a vertex with the purple body and would require a hinge joint to constrain the rigid bodies to move correctly with respect to one another. Instead of including joint constraints in our solve, we modify the BFS and we don't add this element to the green rigid body. We do this by having the BFS greedily claim vertices for each rigid body and preventing two rigids from claiming the same vertices. Nevertheless, we note that hinge avoidance typically happens just moments before the adjacent element are also identified for rigidification, leading to the proper creation of a single rigid body at the appropriate time. If the strain rate is below threshold only briefly, then we would like to avoid rigidification. For instance, the elastic potential energy maximum at the bottom of the swing of this cantilever. We do this by waiting to see the strain rate below the threshold for several steps before rigidifying. We use 3 steps as the criteria in all our examples. Rigidification can now work on some high compression scenarios, like this box rigidifying while sliding through the funnel. Here we see rigidification of elements for a rotational motion, and it is interesting to note that adaptive rigidification allows better preservation of momentum than standard FEM for stiff meshes. We must allow rigid bodies to become elastic again when necessary. For instance, new contacts, elastic waves, user interaction, and so on require elastification. So, which element need to become elastic? A perfect oracle for predicting which element will have non-zero strain rate in the next step could be to simply solve the full elastic system, but this is expensive. Instead, we propose a cheap solution. We use a single iteration of a preconditioned conjugate gradient to inexpensively compute an approximate change in the velocities, from which we can compute approximate strain rates. These approximate strain rate identify the elements that need to become elastic. In this example, we can see color-coded regions that would elastify based on 4 selected thresholds. Here, the blue line is a small force applied at a vertex. With the force applied at different vertices, the oracle appropriately identifies local regions of elastification, small or large, based on the threshold. This preconditioning is critical for elastifying distant regions. In contrast, without preconditioning, a single iteration of conjugate gradient can only propagate information to adjacent nodes following the sparsity structure of the elastic solid. We precompute an incomplete Cholesky factorization of a constant Hessian approximation. Our oracle does a good job at predicting elastification thanks to this preconditioner, even with only a single iteration of conjugate gradient. The oracle must also be contact aware, like when new contacts are created when this armadillo hits the ground, but also when existing contact forces are changing. For existing contacts, we can simply reuse the forces from the previous time step, that is, the contact solver's warm start values, and include them on the right-hand side of the PCG solve. However, new contacts require a bit more work. We solve them approximatively as elastically decoupled bilateral constraints, and then include them on the right-hand side of the solve. Here is a closer look at elastification for new contacts, and the variation of region of elastification due to the impact magnitude. The second bounce of the bowling ball produces a small force on impact, and in turn creates a smaller localized elastic region on the mattress. Here we see an example of elastification due to an elastic wavefront propagating through the thin noodle. Finally, here we see an interesting example of elastification due to a rotational motion known as the Zanibekov effect or the tennis racket effect. This model is composed of a soft and light region and two stiff and dense regions. At the start, the object is rotating as a rigid body about its unstable axis, but stresses build in the stem as it tumbles, leading to an elastification of the stem, which then proceeds to stretch and bend. How do we set our thresholds? We can get some intuition by looking at the histograms of the strain rate and approximate strain rates. Here, the histogram on the left shows the strain rates of elastic elements, while the histogram on the right shows the approximate strain rate of elements within rigid bodies. We set the elastification threshold to be an order of magnitude bigger than the rigidification threshold to account for the oracle's approximation error. Choosing the threshold allows us to tune what is more important, the visual consistency or the speed of the simulation. To compute visual consistency, we run a test simulation of a damped cantilever under gravity, which receives a force on its free end after it comes to rest. The error, in comparison to the fully elastic ground truth simulation, is computed as the maximum vertex distance over all time steps. On the left, we see a subset of simulations we computed for this speed accuracy trade-off comparison. While at right, we plot the log of the max error and the inverse speed-up factor. The x-axis is the elastification thresholds used. Notice the clear correlation between speed-up and accuracy across different thresholds. Here is a different threshold comparison and a more complex scene demonstrating behavioral similarity across thresholds. Notice how the wheel falls on the same side at about the same time. When designing a scene and selecting parameters, there are a few things to keep in mind. Damping reduces deformation and increases the rate of rigidification, leading to faster speedups. Stiffness leads to larger and longer-lived oscillations, while the numerical damping in stiffer examples as them come to rest and rigidify earlier. We observe very similar rigidification patterns independent of the resolution of the mesh. However, at the top, a very coarse mesh rigidifies more quickly because of resolution-dependent stiffness and numerical damping. The strain rate is a material-independent measure of elastic deformation. It is perfect for heterogeneous material models, like this elastic block with alternating stiff and soft regions. Because the stiff regions deform less, they typically have lower strain rates and naturally rigidify more easily. Here, the stiff green regions are orange when rigid, and the soft blue regions become pink when rigid. When pulling on this soft region, notice that the soft region becomes elastic and the stiff part remains mostly rigid. In contrast, pulling on the stiffer region elastify both the stiff elements and the adjacent soft parts. Here is another heterogeneous example in 3D. The pills have two parts. The white half is softer, and as you can see, they deform as they hit the walls. The red half is stiffer and rarely elastifies in this scenario. See the pills rigidifying while sliding down this distributor that simulates on average 13 times faster than the full elastic simulation. Finally, look at this forest. Each tree is a rigidified phylant element model ready for dynamic deformation. We have presented a new adaptive method that uses on-the-fly rigidification to accelerate deformable object simulation, and is readily applicable to large-scale virtual worlds. Our method is faster than standard non-adaptive methods in all of the examples presented, and in many cases dramatically so. This is accomplished without sacrificing visual agreement with fully deformable methods. We can finally be free from forced modeling choices because our method will correctly adapt any given model based on the emergent physics of the simulation. Feel free to download our code, which is available on my website. Thanks for watching, and see you next time.